Hey everyone, this is Professor Mankowski. This is our first question on the worksheet for Chapter 8. So pause the video if you need for a couple minutes, read through the question. So inside the question, they're telling us that if you chew gum, you're going to be doing about 8 sticks a day. And the Wrigley company has been making chewing gum for years, operating on the assumption that that's the real number, 8 sticks a day. And it looks like there's this researcher, the researcher gets the idea that people are chewing more gum than that lately. And they go and they do a sample to try to find out if it's true. Now, if you're the Wrigley's gum company, this would be really important information for you to have because you want to pay attention to how much people are using your product. And if it turns out that the daily usage is going up, you might want to start making some changes on packaging and production. So when we eventually go and look at that sample average, the sample average is coming back as 9 sticks per day. Now, we have to look and say, well, 9 sticks a day, is that significantly different than 8? We know that when we take the sample, remember, we're assuming that the population average really is 8 sticks a day until we get enough information that's going to contradict that 8 sticks a day. But again, we're assuming that when we start the sample, the population average holds at 8, and we also expect a little bit of natural fluctuation around the 8. That's due to sampling error. If we can show that 9, the sample average, is far beyond what you can explain with sampling error, then that's enough evidence for us to say the null hypothesis is not true anymore. Okay, if we're doing a population, if we're doing a hypothesis test for a population average, our big consideration is, do we do a z-test or do we do a t-test? So where do we find that out? We have to start to pay attention to the standard deviation and see where it came from. In this case, they're mentioning the standard deviation in context of the population. They're saying the standard deviation of the population is 1. So right away, we know that we're going to be doing a z-test. What I'm also going to start to do is I'm going to start to label some of the information on the sheet here that we've just identified. We know the population standard deviation is 1, so I'm going to go ahead and write down that 1 is my sigma. I can also figure out that my random sample size was 36 gum chewers, so I'm going to indicate that 36 equals my sample size, or n. And other information I know from the question, they gave me, in the context of that 36, the mean number of sticks chewed per gum was 9. So because that mean number of sticks of 9 is connected to the information that they gave me with my sample, I know that my I know that my 9 is going to be equal to my x bar for sample average. Okay. The other average that they gave me in the question was average number of sticks chewed as 8. And I'll write this a little bit better. Now the 8 is not at all connected to the information that's in the sample, so it must be true that 8 is going to be my mu, or my population average. And the only other information that they gave me inside the question was the 0.05. Which is right down here. And the 0.05 is mentioned right with alpha, so I'm going to go ahead and label that as my alpha level. And now I have all the information that I need to go and start my null hypothesis and my alternative hypothesis. I'm going to write in here my HO and my H1. My null hypothesis is going to follow exactly the same format it always is. It's going to be mu set equal to my population average, which is 8. For H1, my key words are going to tell me that they're expecting the number of sticks chewed. They're asking if it's actually greater than 8. And that's given to me right here. Is the number of sticks chewed really greater than 8? So that's going to tell me I'm looking for a right tail test. And by the way, worth mentioning is always look at the context clues when you're trying to set up your H1. The big mistake a lot of people make, a lot of students will take a look at in their given information, their X bar, and they'll compare that to the 8, and oh, my sample average is higher than my population average, so I must be doing a right-tail test. If you do that, you're going to get really burned on the two-tailed test because it's going to get you all mixed up inside the question. So again, just make sure you use context clues, non-numerical information to figure out what you're going to do for your H1. Okay, now I'm going to start to set up for my critical values. I'm going to begin with a curve sketch here. And since I have a right-tailed test, I'm going to go ahead, I'm going to sketch my critical region on the right side of my curve. And I'm going to label this my critical region for alpha equals 0.05. Okay, now what I have to do is look in my Z table, and I have to find what's the Z score that matches the upper 5% of my curve region, and that's going to be 1.65. That's going to be my critical value. So what this is telling me is when I eventually look at my sample average, I can reject the null hypothesis if the sample average is 1.65 or more standard deviations away from the population average. And now I'm ready to go ahead and run my Z formula. I'm going to put that on the side here. I'm going to fill this in. And when we calculate this out, we're going to get 6. Now I'm going to take that 6, I'm going to compare it to the curve. I need to see if it fell in my critical region. And my 6 is on the far right side, all the way over here. And now I can apply my decision rule. My decision rule tells me it's safe to reject a null hypothesis if my test value, or the 6, if my test value landed in that critical region. Because I'm firmly in that critical region, I'm going to go ahead and I'm going to say I reject my null hypothesis. And my summary sentence would be that it appears the average number of sticks chewed has actually increased. They've also asked me a part B here. Do you think the company should plan on making any production changes in light of your hypothesis test conclusion? My answer to that is going to be yes, because they found out that consumption has changed. Okay, we're going to go ahead with question number 2 here. Pause the video, read through the question. In question number 2, they're telling us that if you're doing a PhD, you're going to rack up on average of $40,000 in debt. And there's an admissions officer that apparently feels that for her graduates, that number is too low. And she's going to go out and she's going to do a sample of 37 alumni to find out if she's correct. Now, a couple really important things about this question as we kind of case the joint a little bit. If she thinks the number is too low, that means she's actually she thinks the average number of loans for her alumni, her students, is underestimated. So it's going to turn out to be a right-tail test, because when she takes the sample average, she's expecting a much higher number. So since we're starting to test population averages, that is a hypothesis test for population averages, we have to be really careful, again, with where the standard deviation came from, because that's going to affect if we're doing a Z-test or a t-test. So let's go ahead and let's track down the standard deviation. It seems to be mentioned as 3,000. Now, the 3,000 is in the context of what happened with the sample of 37 people. What that means is, even though they didn't come out and tell us the standard deviation was a sample, we can infer that the standard deviation came from the sample. So that's where we have to use critical, rather keywords in critical thinking really carefully to figure out, do we have a Z-test or a t-test? Because we're using the sample standard deviation, that's going to automatically bring us to a t-test. So let's go ahead and let's write down what we just found out on the side. before we even start to do formulas and calculations, we're just going to list all of the given information, all of the numbers, along with their symbols, so that we'll have them for later reference. I'm going to put off to the side here, my 3,000 is going to be my S. Now, inside that sample, they also mentioned the sample was size 37 alumni. So I can put in my 37 is going to be my sample size N. And they're also telling me that $41,000 was the average of my sample. Well, I'm going to take that $41,000 and now I'm going to go ahead and I'm going to label that 41,000 my X bar. All right, and there's only one other average given in the question. At the top, they tell me the average amount of loans for completing a PhD program is $40,000. Since we've already used up our X bar, it must be the case that that 40,000 is our population average. I'm going to put in $40,000 equals my mu. And the only other number they mentioned was 0.05, and in the same sentence, that's defined for me as alpha. So I'm going to say 0.05 is my alpha value. Okay, now since we're going to end up using the t-distribution, we're going to end up needing our degrees of freedom eventually. So one last thing that I'm going to do is add in, next to my 37 sample size, my degrees of freedom is going to be 36. Okay, let's start to set up for HO and H1. My null hypothesis is going to be mu set equal to my population parameter, which is $40,000. And because of the key wording, the admissions officer felt that that number was too low. That lets us know that we have the right tail test. And now it's time to get our critical values. And remember, we're on the t-test this time, not on the z-test. So for the t-test, we're going to need a couple of things. So I'm going to write critical values for alpha equals 0.05 and 36 degrees of freedom. And I'm going to do a curve sketch. And my critical region is going to go on my right side of the curve because I'm using a right tail test. So if we look at our t-charts, let's find out what our critical value is going to be. 1.686. Okay, so that's going to tell me that I can reject the null hypothesis if my sample average lands 1.686 or more standard deviations away from the population average. I'm going to do my t formula right now. T equals x bar minus mu, and then on the bottom, I have to remember that I'm switching back to my S. And I'm going to go ahead and calculate that out and see what I get. I'm getting exactly 2. I'm going to do that in a different color. I'm going to redo the calculation, make sure it's correct. Okay, getting the same thing. So now I have to take that test value and I have to consider that in my curve and find out, did it land in my critical region? And the 2 is going to be to the right of the critical value. So now when it comes to apply my decision rule, if my test value landed in the critical region, I've got enough information to say that I'm going to reject my null hypothesis. I'm going to go ahead and I'm going to write in reject HO. So my summary sentence would be that it appears there's enough information to show that at this particular college, the PhD students are racking up a higher than average amount of debt. And second part of the question right here, they've asked me, was the difference of the population average 40,000 and my sample average due to sampling error? And the answer to that is no. If you landed with your test value in the critical region, that means that the difference between your X bar and your mu was much more than what you can explain with sampling error. And that's why we ended up rejecting the null hypothesis. Okay, let's go ahead and look into question number 3. Pause the video if you'd like for a couple minutes and read through the question. Okay, so let's see what's happening in question 3. Looks like IATA is telling us that if you have an airline and the airline lands, the passengers get off, it takes about 50 minutes to turn that airplane around and get it to take off again. And turnaround time means that to get the passengers off, clean up the airplane, reprogram the flight, reprogram the flight computer and get the plane back on the runway to take off again. They refer to that as turnaround time. And the airline has a pretty strong interest in seeing if they can reduce that turnaround time, because if they can reduce it, it means they can get more planes to take off in one day and they can be more profitable. And they've gone ahead, and Delta's done this experiment where they try this system of assigned seats, and they want to find out if that's going to make any kind of a difference. So they do a sample of, looks like 40 different aircraft, and they try this unassigned seating system, and it turns out the average time drops to 47 minutes. What we have to find out is, was that time different than the 50 minutes? Like, did that really create a big difference? Because we're testing a population average, first thing that we're going to think about is, do we do a z-test or do we do a t-test? And I can solve that problem by going ahead and finding my standard deviation. If the standard deviation is from a population, it's going to be a z-test. If the standard deviation came from a sample, it's going to be a t-test. And it looks like they're telling me the population standard deviation was 7 minutes, so I definitely know I'm back to doing a z-test. I'm also going to go ahead and on the side of the paper, I'm going to start to write down some of the numbers they gave me. I know that 7 is going to be my sigma, my symbol for population standard deviation. And now I'm going to go ahead, I'm going to take a look and see if I can find the information they gave me about their sample. They mentioned that they looked at a sample of 40 flights, so 40 must be my n. I'm going to write down 40 equals n, my sample size. And they mention another average in context with that sample of 40, the average of 47. That's letting me know the 47 is going to be my X bar. Okay, the only other average they gave me in the question was a 50. And since the 50 is, of course, not mentioned in the context of the question, of the sample, that tells me that 50 must be my population average mu. And in the last part of the question, they asked me to use alpha of 0.01. So I'm going to go ahead and write in 0.01 is going to be my alpha level. And now I have enough information, I can start doing my hypothesis test. So I'm going to put in a HO and an H1. I'm going to label my null hypothesis, my mu is equal to 50. For H1, the keywords they gave me is the turnaround time different. So that lets me know I have a right tail test. I'm going to put in here, sorry, not a right tail test, a two tail test, not equal to 50. And it's worth making a really important point right here. A lot of people will try to figure out what to do for their alternative hypothesis just by looking at the given information over here. And what a lot of students do that really screws them up in a two-tailed test, they'll take the sample average and they'll compare that to the population average. And, oh, good, 47 is less than my 50. I know I'm doing a left-tail test. And this is exactly where it's going to get you all mixed up. That's why it's critical to look in the keywords to figure out if you're doing a right tail, a left tail, a two-tail test. Don't look at your symbols and numbers attached to the symbols. Okay, so now let's go ahead, let's work on our critical values. I'm going to do a curve sketch here. And what I have to do, because I have a two-tailed case, is I need to take my alpha and I need to split it by 2. So I'm going to go over here and I'm going to say, let's put in big red letters here, two-tail. So I'm going to use my alpha over 2. So it's going to be 0.005. I'm going to put a region equal to 0.005 on both sides of my curve. Two tails is 2 critical regions. And when we look in our z-chart for our critical values, we're going to find our plus and minus 2.58. Okay, now we're going to go ahead, we're going to start to run our z formula. I'm going to see what I get on my calculator here. I'm getting a minus 2.71. I'm going to do that in a different color. I'm going to double check the calculation. Okay, negative 2.71 it is. Now I'm going to take that minus 2.71 and I'm going to compare that to my curve. I need to find out if it hit the critical region, and it's going to be all the way over here. Here's my negative 2.71. So my decision rule will tell me if my test value, my negative 2.71, landed in the critical region, I can reject the null hypothesis. So in bright red letters, I'm going to say I am rejecting HO. And my summary sentence would say that it appears there's enough evidence to say that the system of unassigned seats actually did make a difference. And there's also a question B. In all cases, a sample average will be always different than a population average. In Delta's case, though, was the sample average significantly different? And the answer is absolutely. If we've gone and rejected the null hypothesis, it definitely means that our sample average was significantly different from the population average. Okay, here we are with question number 4. So take a minute to read through the question. I'll press pause if you need to. And this one is about popcorn. And they're saying Redenbacher, Orville Redenbacher, he's been operating, he's been saying for years that the average number of calories in a serving of his popcorn is 75. And there's this person that comes along, this nutritional expert, and they're actually going to try to prove that the number of calories is different in each serving. And if they're right, that could be really bad news for the popcorn company, because Think of the nutrition facts on all the food that we buy. If it turns out they've been putting a number of calories down that's incorrect, that's going to be really bad publicity for the company. So our nutritional expert ends up with a sample of 50 servings of popcorn, and they found 78 calories. So we have to figure out, was the 78 calories actually different than the 75? Is it significantly different, meaning beyond what you can explain with sampling error? So first thing that we're thinking about, just like in the last video, is we want to track down where did the standard deviation come from, because that's going to drive whether or not we use a z-test or a t-test. And in this case, they're telling us population variance of 49 calories. So two important pieces of information we get from that right away. First is we know that the population variance is 49. So we have to be really careful, and we need to put in that this is the variance. Remember, our formula is going to need the standard deviation. So a really important step is we have to take the square root of this. I'm going to put in here sigma, then is going to equal the square root of 49, which is going to be 7. Okay. It also lets us know, because we have a population variance, that we're going to end up using the z-test again. And I'm going to go ahead and I'm going to write down some of the other information they've told us. They looked at 50 samples. So that means 50 is going to be our sample size. I'm going to write that information down also. N equals 50. And they told us that the average of that sample was 78. So 78 must be my X bar. And the only other average that they gave us was the 75. And that's clearly not mentioned within the context of the sample. So that reveals to us that the 75 is our mu. We're going to put in here mu equals 75, and we'll put in our alpha level to finish things off. So pause the video, see if you can figure out the HO and the H1. Okay, so our null and alternative hypothesis ends up being mu equals 75 for HO and H1 not equal to 75, and that's a two-tailed test because they're asking us if the number of calories is actually different. So I'm going to put in here two-tailed test. And now we're going to set up for our critical values. And because we have two-tailed test, this is the part where we're going to have to go ahead and split our alpha. So I'm going to say alpha divided by 2 is going to be 0.05 divided by 2. And let's do a sketch. I'm going to label 2.5% on the right side and 2.5% on the left side. And if we look at our Z tables, our critical values are going to come out to be plus or minus 1.96. Okay, so now we're going to go ahead and we're going to calculate our Z formula. Okay, so pause the video for a few minutes, see if you can get the Z value calculated out, and let's see what we get for the T value. I mean, for the Z value. Okay, so our Z value is going to end up coming out to be 3.03, and I'm going to map that on my curve, and that's going to be to the right of my critical value. So that's going to let me know that I can reject the null hypothesis because my test value landed in the critical region. So I'm going to say reject HO. Okay, so for a summary statement, I could say that it appears the number of calories in the popcorn is actually different than what Orville Redenbacher has been saying. And now let's go ahead. Let's take a look at the other questions they asked us. Well, they wanted to know if Colonel's experiment was substantiated. And since we rejected the null hypothesis and determined that the number of calories was actually different, yes, Colonel's experiment is substantiated. And they've asked us if the alpha level increased, would our critical region become larger or smaller? That would make the critical region become larger because as alpha goes up, we're going to be trapping more area for our critical region. Okay, this is going to be our last question here, and this should actually be, this is not question number 1. Okay, so pause the video for a couple minutes, read through the question. Inside the question, they're telling us that if you own a cell phone bill, according to industry executives, if you own a cell phone, you're going to be paying about $50.07 a month. And there's this irate customer, Ned Flanders. And Ned Flanders starts to think that the average cost is underestimated by these executives. They're lowballing it, probably because they want people to sign up for service. So he's going to go out, he's going to try to prove that he's correct. And Flanders gets a sample of, it looks like 5 different people. He's going to look at their phone bills and he's going to try to take a look at the average and show that it's significantly higher than $50.07. And our job is to figure out if Flanders is correct or if he's incorrect. Now, the one thing that makes this question kind of scary is that they gave us a whole sample, and it looks like we've got to do all this work on our own to mine out all the information we need for the hypothesis test. Because the only number they pre-calculated for us was the average phone bill is $50.07. So the good news, though, is it means if we have to calculate everything that we need from the sample, that's telling us that we also get the standard deviation from the sample. Automatically, we know that we're going to be using the t-distribution then. So let's go ahead and let's start to write down some of the information that we know. We know the sample size is equal to 5. And since we figured out that we're going to be using the t-distribution, probably a pretty good idea to write down that our degrees of freedom is going to be equal to 4 because we'll need that when we read our t-chart. The sample average comes out to be, let's see what that calculated out as, 53. And the sample standard deviation is 1.58. Now, definitely practice calculating the standard deviation because you're almost definitely going to have to do that on the test. And there's lots of videos in earlier in Chapter 8 and Chapter 7 that'll give you a walkthrough on how to calculate the sample standard deviation. Other things that we're going to record, we need to know the population average. And the population average is bound to be $50.07 because that information is not at all connected to the sample. So we're going to say mu is equal to 50.07. And our alpha is 0.05. Okay, so pause the video, see if you can think of what HO and what H1 are going to be. Okay, so for our null hypothesis, mu is going to be equal to $50.07. For the alternative hypothesis, the keywords inside the question that help us figure out what to do is the average cell phone bill higher? So that's going to trigger us to a right tail test. And now we're ready for finding critical values. And I'm going to put in critical value for, since we're back on the t-test, not only alpha equal to 0.05, but also degrees of freedom 4. I'm going to make a curve sketch here. And that critical region is going to go on the right side of our curve. And the critical value is going to be 2.132. Make sure that's correct on my chart. Yeah, 2.132 is our critical value. And now we're going to go ahead, we're going to launch our T calculation. So pause the video just a minute, get some practice calculating out that T formula, and let's see what we get. Okay, so when we do our T statistic, or formula out, we get 4.14. And I'm going to see where that falls on the curve. And that's clearly falling into the critical region. So my decision rule is going to say if I landed in my critical region, I have enough evidence to reject the null hypothesis. So I'm going to put down that I am rejecting HO. And my summary sentence would be that it appears that Flanders is actually correct. The average cellular phone bill really is higher than $50.07. And if I look at the question part B here, could the US wireless phone industry be subject to bad press if news of the findings were leaked to the public? The answer is yes, because it means that the executives are giving a average phone bill that's a lot less than what it really is. So it's almost like deception. And part C, they've asked us, if the standard deviation of the data set were to decrease, would the amounts billed become more or less uniform? If our standard deviation is going down, it means all of the numbers in the data set are converging on the average or getting very close to the population average with very little gaps of space in between from one number to the next. So that would mean the data set is becoming less uniform, so the amounts billed would becoming less uniform. Or actually, sorry, the amounts billed would be becoming more uniform, because as the standard deviation goes down, the data set values are becoming closer to the average. That means they're becoming more similar because there's less gaps in between the numbers. So the amounts billed would becoming more uniform, more similar to each other.